This is video 5 of section 2.3, working with complex fractions and absolute value and squeeze limits to evaluate limits that are of an indeterminate form. So we're picking up with example 5, and why don't you take time now to try to complete the limit, pause your video, and try the absolute value of 2x over x. Recall that you have these notes. I would like you to be filling out the notes as you're going to have to submit them for homework. So again, we are on section 2.3. This is video 5, and I expect we'll probably have 2 more videos in this section. So try this, example 5, and pause your video, come back and check your answer. Okay, with example 5, we're going to find the limit as x approaches 0 from the left and the limit as x approaches 0 from the right. Clearly, I can see that with the absolute value, I'm looking at where the absolute value of 2x, I'm saying 2x is going to change sign on the interior. So if x is greater than 0, then this expression is going to be worth 2x. But if it's less than 0, the expression is going to be the opposite of 2x. So keeping that in mind. So I'm going to take the limit from the left and the limit from the right separately. So I take the limit as x approaches 0, 0 from the left of the absolute value of 2x over x. So that will then be equal to the limit as x approaches 0 from the left of negative 2x over x, which is equal to the limit as x approaches 0 from the left of just negative 2. So that's going to have a value of negative 2. Then if I take the limit as x approaches 0 from the right of the absolute value of 2x over x, that will be equal to the limit as x approaches 0 of 2x over x, which is equal to the limit as x approaches 0 from the right of 2, which is just the value 2. Now, you may ask, well, the limit of a constant. There's no x to change the value, so recall what you're looking at. You're kind of looking at a graph of this. Y is equal to 2x over x, and y is equal to negative 2x over x, producing those values. So they're horizontal functions, so the functions always take on the value when x is less than 0, take on the value of negative 2. When the function is greater than 0, this is on the right, it'll take on the value of 2. Therefore, it's approaching the value of 2. It's always 2 to the right of 0. To the left of 0, it's always negative 2. You might want to try to put these in your grapher. All right, example 6. Find the limit of a piecewise function. So 2 different parts of this function. So in the first one, we have the limit as x approaches 3 of f of x. And f of x is given as a piecewise function. So the first thing that I want to do is say, well, what is this? What does it look like as a graph? But I could say, okay, well, the limit as x approaches 3 of the line, I just want to see what this looks like. It'll look like this until it gets to 3, right? You know that this is y is equal to 1/2 x plus 2. And when you get to 3, you can't use that point, is what that first part is saying. So at 3, if you plug 3 into the equation, you're going to get 3.5 or 7/2. I'll just leave it as 3.5. But then you know the second part of it is saying that the function value is 2 when x is 3. So I'm going to put that down here. So you have this point that's just sitting out of there, a point of singularity, as they say in math, and it's just sitting by itself, okay? So we look at the graph, and you really could just do a direct substitution and say the limit as x approaches 3 of f of x is equal to 2 plus 3 over 2, which is equal to 3.5 or 7/2. 4/2 plus 3/2 is 7/2, 3.5. The point in the bottom, as you approach the value x is equal to 3, the point in the bottom does nothing in terms of the limit. Okay? So let's look at the next problem. Find the limit for the piecewise function here. Now remember, not all piecewise functions are continuous. The last one had a hole in it. Let's see what this one looks like. So we know we have the graph of x squared between -2 and 3. So what I'm going to do is just do a really quick graph of what this looks like. And you guys know 1, 2, 3, 4, 2, 3, 1, 2, 3, 4, 5. So here's your y-axis, your x-axis. We're not putting a lot on here. So we go -2, -2, 4. And we're only going from -2 to 1 for the x squared graph. Put a hole there. Point here, and we're going to connect those points. So we have that graph. And then for the second part of the graph, we'll go green, and we have the line x plus 1. Now, it's a simple little interval. You're only going from 1 to 2. So 1 plus 1 is 2. So if we plug in 1 plus 1, that gives us 2. So when x is 1, y is 2. Put that here. And then when x is 2, 2 plus 1 is 3. So here's 2, so up at 3. So our graph amounts to this, and that's it. So now graphs always make tons of sense when you're looking at limits. So we want to look at the limit as we approach 1. So from the graph, the limit as x approaches 1 from the left. From the graph, you can clearly see what you're doing. But say we didn't have that. Well, here I'm seeing here's -2 to 1, and then 1 to 2, right? So this is definitely the left portion, and this is the right portion. So I'm going to say, okay, here's the left hand, here's the right hand, and all I'm going to do is say, okay, I'm approaching 1, then it's going to be 1 squared, which is 1. And oh, I could have color-coded that too. Here, let me color-code it. All right, so that one's red, right? Yeah, probably more time than it's worth, but there it's red now. Now let's go green. And green, 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 green. Okay, so now let's take the limit as x approaches 1 from the right of f of x. So that means I'm going to use the right-hand portion, which is equal to then 1 plus 1, or that's equal to 2. Kind of what the graph said here. So we conclude, therefore, the limit as x approaches 1 of f of x, come on folks, say it, that's from the left, that's from the right. So we're going to say the limit does not exist because, upside down triangle, the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right. And end of story there. Okay, I'm going to make this video a little bit shorter, and I'm going to pick up with example 8, and then we'll have a few more problems to do with the squeezing theorem, and that will be the conclusion of section 2-3 of chapter 2, limits. See you later, guys.